Okay, let's go ahead and get started. I hope everybody can hear me. And we're going to continue our discussion on the brain today. We left off at the corpus quadrigemina, and you should have seen that in lab this week when we went through the brain, the structures of the brain. Are there any questions on anything at this time? Okay, I'm going to assume that you can hear me, and I'm going to go ahead and open up the PowerPoints. Okay, so last thing we talked about was the corpus quadrigemina. The corpus quadrigemina is two reflex areas in the dorsal surface of the midbrain. Remember, the midbrain is the top of the brainstem. And so we have the midbrain, we have the pons, we have the medulla oblongata. The corpus quadrigemina is on the dorsal side of the midbrain, just the opposite of the structure that's shaped sort of like a bird, if you will, in the cross section. So we have two sets of bulges, bumps, enlargements, protrusions here, called the superior colliculi and the inferior colliculi. Superior is called superior because it's on top. That's the usual naming practice for any structure. If it's above another one, one's superior, one's inferior. So the superior colliculi is a visual reflex center that allows you to turn your head essentially in the direction of any sudden movement that you might pick up with your peripheral vision. You know, as we say, out of the corner of our eyes. The rods that are located on the edges of our retina are going to detect this motion. Rods are very sensitive to motion. You know, they do motion well, they do dim light well. And so since they're on the edges of our retina, they pick up motion on the edges of our visual field very well. So we turn our heads in the direction of a sudden movement, a sudden action, a flash of light, something that we would detect on the edge of our peripheral field, or as we say, in the corner of our eye. And we turn our head usually in that direction. The inferior colliculi, it is directly below that, and it is a sound reflex center. You hear a loud noise, you turn your head in the direction of the noise. Someone calls your name, and you turn your head in the direction of someone calling your name. Whether it's you or someone else with the same name, it doesn't matter. You still turn your head. We all do that. And whether it's a loud noise, whether it's an ambulance siren, a fire engine siren, a police car siren, a loud bang, or whatever, you're going to turn your head in the direction of the stimulus, the auditory stimulus. It is a reflex designed to protect us. Now, the superior colliculus is designed for us to respond to any kind of visual input, that not just in our peripheral field of vision, but also like when we're watching objects move. It allows us to track objects, like when we're throwing a ball back and forth, or when we're driving and we're estimating the movement of vehicles at an intersection, when we can safely pull out and when we shouldn't go out. And where it's located, we see it here. It is at the base of the brain, directly below the occipital lobes. The dorsal dorsal portion of the midbrain is directly below the occipital lobes, directly behind the pineal gland. The pineal gland secretes melatonin, which helps to regulate our day and night cycles. And it is above the cerebrum. The cerebellum. This is the cerebellum down in here. And these are the occipital lobes up here. So, okay. Now below the midbrain, we have the pons. The pons is an oval-shaped structure. It is pons is essentially Latin for bridge or crossing over. At the pons is where most of our spinal nerves that are moving up the spinal cord, of course we're calling them tracts, will cross over from left side to right side and right side to left side, because our brain has contralateral control, meaning that the right side of the brain controls the left side of the body, and the left side of the brain controls the right side of the body, if I said that correctly anyway. So we have this opposite side control because the spinal nerves cross over at the pons. And there's some other reflexive areas in there too, but mostly it's where we see a lot of our nerves that are coming up, the tracts coming up in the spinal cord cross over to go into various locations in the brain. Now below that, below the pons is the medulla oblongata. Now where the medulla oblongata ends and the spinal cord begins is sort of problematic because they just sort of run into each other. But we have, this is where most of our sensory and motor tracts are present. Sensory tracts coming up and motor tracts going down go through the medulla. We have an area called the cardiovascular center that controls the rate of our heartbeat. It doesn't control the heartbeat, the heart controls itself, but we can control the frequency. We can tell the heart, the cardiovascular center will tell the heart rate to speed up or slow down, depending on what we're doing. It will tell our blood vessels to open up or to close, depending on what we're doing. We have a respiratory center that tells us when to breathe and how fast to breathe. You know, a normal breathing rate is once every 4 seconds. Well, we may have to breathe faster, or we may want to breathe slower. And that respiratory center in the medulla controls that. The medulla also controls our swallowing reflex. It directs information to the hypoglossal nerve, which goes down through the hypoglossal canal on either side of the foramen magnum. Everybody remembers that from the bone lab. The ability to swallow is controlled by the medulla. A patient that has had some sort of accident in their brain, a stroke, trauma, a contusion, if you will, any of those that affect the medulla may affect their ability to swallow. Our reflex centers for coughing and sneezing are also located in the medulla. So the medulla is a pretty busy structure for us here. Okay. Now, within the brainstem, running through all parts of the brainstem, we have a structure known as the reticular formation or the reticular activating system. Now, this formation, it does a couple things for us. The first thing it does is it filters out a lot of extraneous background stimulus, background noise, lights, motion, irritations. You're not paying attention to the tag in the back of your shirt, at least you weren't until I pointed it out to you. You're not paying attention to the pressure of your seat onto your back, or are your shoes tight, or are they comfortable? You're not paying attention to the presence of the clothes on your skin, or the light in the room, or how loud or how quiet it is, or any kind of background noise. We filter all that out. It takes all this stimulus that's coming in, the low-level stimulus that's still there, but puts it off to, sort of in our subconscious. So we're not really paying attention to it, even though we are. And so, but what it will do, the reticular activating system will let us know when a stimulus is important. When we have a sensory input that is important, we'll become aware of it. Consider this: you're at home at night and you're sleeping, and your air conditioner goes out, or your heater goes out, and you no longer hear the sounds of the AC kicking on and off, or the heater kicking on and off. Now, just because we're asleep doesn't mean that our ears don't work. Our ears work fine while we're asleep. We just don't process it because we are sleeping. However, that information is still coming in. And we are used to the background sounds of the AC or the heat cycling all night long. It's part of, we don't pay attention to it anymore until it stops making that noise. The absence of that sound is detected by the reticular activating system so that and alerts us that something's wrong. The AC's out, or the heat's off, or the power went out, because the house suddenly gets too quiet. All the little background noises that you normally just put in become what do we call the background sounds, or the background stimulus are no longer there, and we detect that. So the reticular activating system, the reticular formation, which runs through the pons and the midbrain and the medulla, which normally damps down all these background sounds and background noises that we, as we like to say, we get used to them. It lets us deal with that. We are listening to everything, but only important signals get through. When you're asleep and your child cries, you wake up because you heard your child crying, or coughing. If you're if you go to your child's school and they're in the classroom and it's a crowded classroom and a child coughs, the sound of the cough that your child makes, and you can identify that right away. That sound right away. Or you're asleep and you hear a loud noise outside and it wakes you up. A noise that you're not used to hearing during the night. Many people sleep through thunder during a thunderstorm. The flash of lightning doesn't intrude. The sound of thunder doesn't intrude. That seems to become part of background to some people. But other noises like a loud crash or breaking glass, things like that, penetrate very easily. So the reticular activating system keeps us alert during the day and alert during the night while we are sleeping. We depend on it to filter out the extraneous background stimulus so that we're not overwhelmed. Because if every stimulus was presented to us as we're receiving it, from all the contact on our skin and all the sounds that we're hearing and all the visual input, we would be unable to process everything. But fortunately, the reticular system is a filter. It will keep us awake to do the things we need to do. It will filter out the activities that we don't need to be alerted to, and so that we just sort of, we don't pay attention anymore to the tag in the back of our shirt. Okay, so that is the reticular activating system. It's a pretty important structure for us. It will wake us up when we need to at night, when we detect odors that shouldn't be there. We detect sounds that shouldn't be there. We detect a temperature change that shouldn't be occurring. All these things are going to penetrate our subconscious, our unconscious state, and we can wake up. And even during the day, we will detect things that we filter out the extraneous and we keep the important. Now, the second largest portion of our brain is located right behind the brainstem. It's called the cerebellum. The cerebellum helps to modify motor activity. Motor signals originate in the cerebral hemispheres. They have to be modified by the basal ganglia, but they have to be refined by the medulla so that we can do things correctly. The medulla also, not the medulla, the cerebellum. The cerebellum contains our muscle memory, the areas where we learn how to do things, and we practice and we practice and we practice. And that allows us to get better at what we do, get better at physical activities. Something as simple as learning to walk when we were a child, an infant. We're learning to walk. We then remember how to do that. The muscles remember how to do that. Riding a bicycle, once learned, that activity stays with us forever. Learning to drive a car, learning to play sports, learning to play different types of sports. What is the most efficient way to do something? We learn that, and we practice it and practice it and get better by storing that memory in our muscles. Call it muscle memory. We learn and get better. Practice makes us better. Doesn't say we're going to make us good. It just makes us better at doing it. So two primary functions: to coordinate balance and equilibrium, to make adjustments in our body's position, to maintain balance and equilibrium. That's the first thing. We are always adjusting our posture so that we are in equilibrium. Remember the writing reflex from lab with proprioceptors? No matter what position our body is in, we will raise our head so that our eyeballs are level with the horizon, so that we can we have a set point, we have an equilibrium, we have a balance, we know which way is up by lining up our eyeballs with some sort of visual horizon. And so that's how we can maintain our balance and equilibrium. And we're constantly adjusting our muscles to do that. The other thing we do is that we can fine-tune our motions and our movements so that they are the most efficient as possible and not some ragged, throw a lot of muscle cells at it to get our arm to move. Well, we refine that to where we get the precise movement we want to have, so that we use the learned pattern of movement over and over again. It gets better, it gets smoother, it becomes much more efficient. So the cerebellum refines our motor activity. It maintains our posture and balance using the large postural muscles. It refines the motion of our skeletal muscles in what our skeletal muscles do. They refine the motion of when we try to manipulate our environment. Now, the cerebellum can be damaged by trauma. If so, we have difficulty in walking and moving. It can be affected by drugs and alcohol. Many people that have used alcohol, if they use it in excess, they find that they may be dizzy, they may have lose their balance, they may have a lack of poor equilibrium, they may have difficulty in motion of any kind. So the alcohol interferes with the ability of the muscle cells in the cerebellum to refine the motor activity. And so sometimes you get excessive actions. Sometimes you get very short actions, and your person that's ingested a lot of alcohol can't walk straight, can't stand up, can't talk clearly, all because the cerebellum is affected. Certain medications will do the same thing too. Certain pharmaceutical medications will, they often have a warning label there: do not drive a vehicle after taking this medication, or this medication is going to make you sleepy. It will reduce awareness. So don't take this medication and try and use complex machinery type of stuff. Now, our brain, when it's active, which it is all the time at various levels, when our brain is active, it's generating depolarization waves, much like the heart does. The heart, we've heard of the term EKG, where we measure a depolarization wave across the cardiac muscle. Depolarization waves, action potentials are all the same. In the brain, we have depolarization waves. We can measure them on a device known as an electroencephalograph. So we're measuring the passage of action potentials through the brain. And these brain waves have some very distinctive patterns. They change with our age. The patterns in a 5-year-old brain versus a 55-year-old brain are going to be different. They can be indicative of damage. They can be indicative of different types of sensory input. So the term brain death or brain dead is determined when it's a clinical condition for death. It's determined if the brain is not generating any kind of depolarization waves. It is a flat, we say it's a flat line. So what do these waves look like? Well, there are 4 categories other than flat line. We have what are known as alpha waves. When you're awake, but you're resting, your eyes may be shut, but you're awake. You're not thinking of anything in particular. We have alpha waves. When we're in that resting state, you see the alpha waves are just sort of a nice up and down action here. You can see it on the red line down there for alpha. So if you're just sitting back and just not thinking of anything in particular, you're probably, if we were to measure you, you would be in alpha waves. Now, the second category, which I would hope that most of us are in right now, are what are known as the beta waves. When you have any kind of mental activity, you're going to generate beta waves. When you're reading, when you're watching TV, when you're watching a movie, when you're driving your car, when you're in class taking notes, when you're doing anything that is more than just being passive, you're going to have beta waves. Beta waves, you'll notice that the peaks of the beta waves are closer together. And we see that occurring here. The peaks and valleys run closer because the action potentials are going faster in here. Now, third category, theta waves. So alpha waves when you're awake but you're resting, beta waves when you have mental activity going on. Third category, theta waves. They're irregular waves. You'll notice down here they have peaks and valleys, but they have sometimes the peaks and valleys are very, the area under the wave is very broad. Sometimes it's very brief. Sometimes these are irregular shaped waves. Now, this is fine in children because a child's brain is all over the place. It just because they're learning, they're opening up and learning all sorts of things, and so we see this kind of irregular wave going on. However, if you see this in your adult patient who's awake, that might indicate something's going on. We generally don't see theta waves in an awake adult. So you hook up the electroencephalograph to your patient, you run the graph, and you see theta waves, and they've been awake the whole time. It doesn't mean there's necessarily something wrong. It means that they're unusual. They might be considered abnormal. Now the question is why? And then the last category are the delta waves. The delta waves are the green ones down there, and they are very broad. The peaks and valleys are far apart. The waves themselves are very broad. This is what we have when when the reticular activating system has damped everything down. We're asleep, we're relaxed. We don't have a lot of action potential shooting across the brain at any one time because there's nothing really bothering us. We're relaxed, we're asleep, we're not consciously awake. In a perfectly healthy adult, delta waves are normal when they're asleep. However, if you have an adult that's awake, we don't want to see delta waves. usually indicates there's some sort of damage going on that has occurred in the brain itself. So, delta waves are fine when we're asleep. They're not fine when we're awake. Theta waves are fine in children. They're not fine in adults. Everybody has beta waves. Everybody has alpha waves. Alpha waves are at rest. Beta waves are when we're active. You would not expect to see theta waves in an adult that's awake. You would not expect to see delta waves in an adult that's awake. So does it tell you what's wrong? No, it does not tell you what's wrong. It tells you that there's something that may be occurring that's wrong. You know, again, it's a non-invasive test. You know, it tells you that might be something wrong. There might be damage, or there's something else going on here, but it doesn't tell you what it is. That's going to take a little more looking. So, okay. So we can look at our EEG, the electroencephalograph, while our patient's awake. We can look at them while they're asleep. Now, what is sleep? Well, we all know what it is when we go to sleep. The classic definition of sleep is a state of partial unconsciousness from which you can be aroused. In other words, you go to sleep, you wake up, you're unconscious, but not so unconscious that you can't respond to some sort of stimulus, a loud noise, someone calling your name, someone shaking you, you know, detecting an odor, detecting an unusual sound, you know, all that. That means that we are only partially unconscious. Now, in sleep patterns, there's only two types. There's what we call REM sleep and non-REM sleep. REM sleep is rapid eye movement. It seems that when we dream, our eyeballs move around underneath our eyelids while we're asleep, and they move very rapidly during dreaming. And you can see the movement through the eyelid. The eyelid is closed, and yet we'll see the motion of the eyeball underneath the lid. So in REM sleep is the dreaming stage of sleep. Non-REM, where we don't have any kind of motion, is the non-dreaming portion. So there are two major types of sleep, REM and non-REM, and we will alternate through these during the night. If we're sleeping at night, we will alternate between REM and non-REM. We have to have REM. Dreaming allows us to relax and recharge our subconscious mind. We have to have REM sleep. Non-REM lets our body rest, but REM sleep allows us to rest our mental activity. We generally start out when we fall asleep, we are going to be in non-REM. Non-REM has 4 stages. We pass through each stage fairly quickly, and after about an hour and a half, we finally move into REM sleep. So we go through these 4 stages. When we first fall asleep, we're getting lower and lower in the stages. By the time we leave the 4th stage of REM, we move into 4th stage of non-REM, we move into REM, and that's when we have active dreaming taking place. Now, this is what REM sleep looks like. Watch the eyelids. You'll notice that they move. The eyeballs are moving underneath the eyelid. Well, that's indicative of dreaming. Perhaps we're using our eyeballs when we're dreaming to see things. Could be. But we have this kind of motion. We don't have this motion when we are asleep, but in non-REM. Something else about REM sleep, we're not paralyzed, but muscle activity is generally inhibited, so we don't act out our dreams. We don't act out physical activity from our dreams while we're asleep. So, we don't fall out of bed, we don't jump up, we don't start waving our arms around, anything like that. So this is what's going to happen in REM. Doesn't mean we're paralyzed. This means that we're inhibited from taking any, we're inhibited from doing what the dream is doing, allowing us to do. So dreaming takes place during REM sleep. Nightmares and what are called night terrors, which are like brief nightmares, occur in non-REM, usually in stage 3 and 4. So if your child has a nightmare, if you have a nightmare while you're sleeping, it is usually taking place. You are in non-REM sleep. They're usually stage 3, stage 4. So, but the giveaway for when it's REM sleep, of course, is the movement of the eyeballs, rapid eye movement. So how long does this last every night? And how well do you remember dreams? Well, we alternate during the night between REM and non-REM. We will alternate. We would go from REM to non-REM and back to REM, all night long. Once we get into REM sleep, and once we finish a cycle of REM sleep, we'll move back to non-REM 4, and then we'll move back to REM. We'll go back and forth during the night. We start out, our first REM sleep occurrence is usually about an hour and a half after we've fallen asleep. It only lasts a few minutes, but then it will last longer and longer. We will move back and forth into this REM and non-REM. So the last REM event may last an hour. The first one lasts about 5 minutes, and then we'll go back into non-REM, and then we'll go back into REM, and we'll get longer and longer each time. Now, do you remember your dreams? Some people do. Some people remember their dreams. Some people, we usually tend to remember the last dream we had before we awaken. Often the last dream that we have is responding to some sort of outside noise or outside stimulus. It's usually the last one that we can remember. Many people have similar types of dreams. A very common dream is a running dream where you're trying to run away from something or run towards something. Many people have falling dreams where they're falling or they're flying. A very common dream that a lot of people have, it deals with academics. And it's a very common dream of, it's the last day of exams and you're trying to get to the classroom to take your test and you can't get there from here. Or you show up in class and discover that you haven't come to class all semester and now you're trying to get everything done in one day. But people that, we find that students and faculty both tend to have dreams along that category of dealing with, you can't find the classroom, you can't find the course, you can't find anything. Is it a nightmare? Is it a dream? It's hard to say. A lot of people call it a stress dream. A lot of things happen in our dreams that we would not normally see in reality. Many people say that when they dream, they dream that they're naked in public and nobody knows. That's a very common dream. So if you have that dream, a lot of people have that. So it's nothing unusual. I've never seen an explanation for it, but it's a dream. So anyway, not something we want to practice for real. Okay, so those are the sleep cycles and the dreaming cycles we encounter. Many of us have the same types of dreams. What dreaming does is allow our subconscious to relax, to recharge itself. And that's very important to us. That's one of the problems with a lot of sleep aids, that allow you to sleep, but not necessarily allow you to dream, because of the presence of the pharmaceuticals that are, put you to sleep. Okay, So we've gotten the cerebellum, we've gotten the brainstem, we've got the reticular activating system, and that took us into sleep cycles and brain waves. Let's move up into the structure of the brain, into the diencephalon. The diencephalon is the cap on top of the brainstem. It consists of the thalamus and the hypothalamus. The thalamus is that structure in green that's shaped like an egg. There are two of them, and the hypothalamus sits below and in front of the paired thalami. The thalamus is responsible for receiving all sensory input into the brain. Everything comes into the thalamus from all sensory receptors except odor. The hypothalamus controls our pituitary gland, and it is the link between the nervous system and the endocrine or hormone system. So there's our diencephalon right there. The third ventricle surrounds the thalamus. There's the hypothalamus there. So the hypothalamus extends on down and connects to the pituitary. This orange structure here is the pituitary gland. So the hypothalamus controls the pituitary gland directly and indirectly. So there are the paired thalami, there and there. Each thalamus is about an inch long, and all sensory input comes into the thalamus. Everything except olfaction, they go through the mammillary bodies. And the thalamus helps us to deal with emotions too, a little bit anyway. But all the sensory inputs coming in through that. And so it relays, visual input comes in here and is sent back to the occipital lobe. Visual, let's see, taste comes in here and is sent to the temporal lobe. Pressure, pain are all routed around the brain as they come in through the thalamus. Now the hypothalamus is directly below this. The hypothalamus is going to extend from the optic chiasma, which is located right about here, all the way to the mammillary bodies, which are back here, these little things right here. And the hypothalamus is, as I said, the connection between the nervous system and the endocrine system. The hypothalamus is a regulator of temperature. It regulates our body temperature. It maintains our constant body temperature. It will help to process smell, olfaction. It will monitor our blood pressure. It will monitor our osmotic concentration, the salt concentration. It monitors, as I said, monitors temperature. It monitors all of our visceral input and somatic input. It gets that directly from the thalamus. So the hypothalamus knows what's going on and can respond by controlling the endocrine system, telling the various glands to release appropriate hormones. What's going to trigger the release of insulin from the pancreas when blood sugar goes up? Well, the hypothalamus is what is monitoring that. So now the hypothalamus connects to the pituitary gland through what's known as the infundibulum. That's that little stalk that's sticking up right here, the little pink stalk. That's the infundibulum. Now the mammillary bodies are the one area back here that are going to relay the olfactory sensations. So they are, olfaction doesn't go through the thalamus. It has its own little section to go through. Now, because I said this already, but let's talk about the hormones for a second. The hypothalamus is going to be the controlling structure of the autonomic nervous system. So all of your smooth muscle, your cardiac muscle, and your glands are directed ultimately by the hypothalamus. It will control the pituitary gland. The pituitary gland has two portions, an anterior and a posterior pituitary, and the hypothalamus will control their actions. It will produce two hormones that get stored in the posterior pituitary. It also will control our response to stimulus as far as anger and aggression and rage. It will help us to deal with pain. It will allow us to enjoy pleasurable activities. It will allow us to have sexual arousal. It will allow us to become hungry and thirsty and how to satisfy that hunger and thirst. It also helps to regulate our sleep cycles. So it does a lot of things for us there. There's our pituitary gland. There's our, now another thing we see, let me go back here one slide. So we had the hypothalamus. Now back here, we have a structure known as the pineal gland. You saw the pineal gland when we were looking at the corpora quadrigemina. Pineal gland is going to regulate our day-night cycle by releasing a hormone known as melatonin. Melatonin tells us to be active during the daylight, and it tells us to be relaxed at night. We secrete high levels of melatonin in the dark, or when darkness occurs. How do we know it's dark? Well, we get visual cues from the eyeballs. The eyeballs tell us, hey, it's getting dark outside. Melatonin levels go up, makes us sleepy, makes us want to rest. It puts us into a day-night biological clock. In the day, the visual cues we get from our eyeballs tell us it's daylight, so we don't make a lot of melatonin. We stay awake until nightfall occurs. So the pineal gland is regulating our day-night cycle. This is what makes it difficult for us when we work shift and we go from first shift to second shift or first shift to third shift, because our bodies are saying, hey, it's dark outside and I should be in bed, because that's what the pineal gland is saying. It's releasing lots of melatonin. That's why it's difficult to sleep during the day if you work at night, because your melatonin levels are getting those visual cues from daylight. And so it's hard to sleep. Whereas at night, it's hard to stay awake because there's no light. So you want to sleep. So it's hard to adapt to that, especially if you're rotating over like a couple of days on, couple of days off type of cycle. Now, the other area we see here is what's known as the habenular nuclei. That's what triggers emotional responses in us when we detect certain odors. That emotional response can be disgust when we smell garbage, for example. If you detect a rotting vegetation or a dead animal along the side of the road, or even a skunk, it's decided to express its displeasure, you have an emotional response to that odor. But they can also be good. You respond positively to odors of your favorite flowers. You recognize them as, oh, I love that smell, of whatever flower, or your favorite food. So you have an emotional response, a positive response, just as easily as you can have a negative response to something else. The habenular nuclei is where odors trigger emotions, because odors and memories and emotions are all linked together. Certain odors will trigger memories and give you an emotional response. You remember the odor of your grandma's favorite biscuits. You loved your grandma's biscuits. You didn't think much of grandma, but you loved her biscuits and you really miss those biscuits. And maybe you miss grandma too, or maybe grandma couldn't make biscuits worth a darn, but you still miss her. And so an odor of baking biscuits triggers the memory of your grandma, and you have the emotional response for good or for bad. So odors and memories and emotional responses are all linked together. Because odors we detect odors once the chemoreceptors are activated and we stimulate that area of the brain saying, hey, that's an odor, then the memory of the odor tells us what it is, and that runs us down the pathway towards the emotions. And so we can have an emotional response. So there's the hypothalamus. I showed it to you on the illustration, but the hypothalamus is, can't see it here. There's the can't see the habenular nuclei. You can see the pineal gland there. The habenula is directly behind it, so you can't see it. But again, the pineal gland right above the corpora quadrigemina, at the tail end of the thalamus. Let me go back and show you this. Because there's the thalamus right there in blue. The pineal gland's back here. Your corpora quadrigemina is there, and you have your habenular nuclei right there. So now, okay, so I've saved the best part here for the end of this. And we're not near the end, but I've saved the best part for this. The cerebral hemispheres. This is where we are located. This is the largest part of our brain. We have two hemispheres, the left and right cerebral hemispheres, divided by the longitudinal fissure, separated by or connected by the corpus callosum. We have the cerebral cortex, the medullary body, and the basal ganglia here. Now, the outer layer of our brain, of the cerebral hemispheres, the term, if you've ever heard the term gray matter or gray cells, it is the outer 4 millimeters of the cortex where we find our gray matter, and that is unmyelinated axons. Well, now you know that unmyelinated axons aren't as fast as myelinated ones, but the distance they have to travel here to send their action potentials down their axons is very, very brief. So the speeds are still instantaneous as far as we're concerned. We're not sending an action potential down for 1 or 2 meters. We're sending it a millimeter or 1/10 of a millimeter, if that. So the speed is still extremely rapid, instantaneous as far as we're concerned. So the outer covering of our brain, the outer layer of our brain is the cortex, and that is where the gray matter is located. And we can see it here. Let's see. Take a look at this model right here. The gray matter is not highlighted, but the area where the gray matter would be located is all along this outer covering right here. This is the cortex. The term cortex and medulla describe the brain and other organs. So this outer layer right along in here is this 2 to 4 millimeter thick layer right here is where we're going to have the gray matter. And that's where we are in the cerebral cortex. That's where everything about us is found. So now the brain is marked, I showed you this in lab. The brain is marked by ridges called gyruses or gyri and sulci. The sulci form grooves. Larger grooves form that we use as landmarks. The longitudinal fissure, of course, is the largest of the landmarks. We also have what's known as the transverse fissure that separates the cerebellum from the cerebral hemispheres. We also have what are known as sulci. The sulci are the smaller grooves, and we use the central sulcus as a major landmark dividing the brain into the frontal lobe and the parietal lobes. Okay, now, so there's our brain. Our brain is divided up into various lobes. The bones on top of the lobes have the same name: frontal lobe, frontal bone, parietal lobe, parietal bone, and so on. So in the frontal lobe, the area in pink, and it's not pink for real, is our motor area. Motor activity is initiated in the frontal lobe. When we do things to manipulate our environment, we initiate those activities in the frontal lobe. Our personality and our behavior comes from the frontal lobe. Our emotions come from the frontal lobe. In fact, our logical brain and our emotional brain are both located in the frontal lobe, and they are always antagonistic to each other. And our memories are in the frontal lobe. The parietal lobe, back here in the blue area, behind this groove right here, which is known as the central sulcus, the parietal lobe deals with somatosensory input from our skin and from our muscles. Touch, pressure, pain, irritation, stretch, vibration, all of that is coming in to the parietal lobe. All this somatosensory stimulus. In the occipital lobe, back here in light blue, back at the base of the brain, the occipital lobe is all vision. This is the visual area of the brain. Input from the eyeballs comes all the way across the back to the back of the brain and is processed in the visual area. And the temporal lobe, on the sides, deals with hearing and smell and taste. So these are the four lobes and what they do. See. Frontal, parietal, occipital, and temporal, right there. Yeah. Now, the longitudinal fissure divides us in half, divides the cerebral hemispheres in half. The central sulcus is a groove and a very important landmark that divides the frontal lobe from the parietal lobe. It is the landmark, because in front of the motor comes out of the frontal lobe. Sensory is in the parietal lobe. The central sulcus is it marks this area. Central sulcus tells us where we have where motor ends and sensory starts, essentially. Central sulcus. Now, two other important landmarks are the ridges in front of and behind the central sulcus. We have what's known as the precentral gyrus and the postcentral gyrus. Now, on this illustration here, the precentral gyrus is marked in blue. That is the ridge in front of the central sulcus. That's why precentral means in front of the central sulcus. So we call it the precentral gyrus. Behind it is the postcentral gyrus, the ridge behind it. The central sulcus is a divider between frontal lobe and parietal lobe. Behind the central sulcus, it's sensory. In front of the central sulcus, it's motor. There is one more lobe that we don't see, and that is called the insula. The insula is deep within what we call the lateral sulcus, down here along the side. I'll show you that here, a better picture here in a second. So here we go. The insula. Down inside, the lateral sulcus is not showing here because this is, but here we have the central sulcus right here. We have the precentral gyrus. This is the frontal lobe. There's the precentral gyrus. There's the postcentral gyrus. There's the parietal lobe. There's the occipital lobe, cerebellum, temporal lobe, and the insula is behind the temporal sulcus, which is right about in here. Okay, so what does the cortex do for us? I'll get back to the insula in a minute here. What does the cortex do for us? Well, three things. The first two aren't very large, covering surface. The areas that they involve are not very large. the cortex, the outer covering, the outer 4 millimeters, the icing on the cake. Motor, voluntary motor actions. Voluntary motor actions, mostly in the frontal lobe. Mostly in the frontal lobe. Sensory, where we recognize, where perception, where we perceive a stimulus, where we have conscious perception of a stimulus. That is mostly in the parietal lobes. Motor and sensory. And the whole rest of the brain, the other 99%, the other 98% of the brain is all about association and integration. Everything below the cortex is information to be used to integrate and put it together. Association areas take stored memories, stored information, past experiences, all, external and internal stimuli to give us a comprehensive picture. And 99% of all the neurons in the entire brain are association neurons. So the bulk of what our brain does is not sending signals out to move something or to receive sensory input. It is to put it together, put that stimulus together so we know what we're doing, or we have a proper output. That's what association allows. That's what integration is all about. It's like pulling up all the ingredients you need to make a cake. The instructions, you have a complete list of instructions of the ingredients you need, and you have to put them together in the proper mix. And you have to follow those instructions to bake a cake and bake it correctly. That's what integration is all about. Okay, so what about the white matter? That's the gray matter. The gray matter is us. It's the 4 millimeters, the outer covering of the brain, the cortex. Now the white matter is all the association areas that are where we have lots and lots and lots of information. Now we communicate to all parts of the brain using these nerve fibers, and they're all myelinated, so they're traveling very fast within the brain. They only have short distances to go. We have 3 types of fibers. We have what are known as association fibers that stay in the same hemisphere and communicate from one gyrus to another. We have what are known as commissural fibers that communicate from one side to another. Now the association fibers stay in the same side. They go front to back, and back to front within the same, within the same hemisphere. Commissural fibers go side to side. Those green things there. That's the corpus callosum, communicating to the left side and to the right side, back and forth. The association fibers stay within each hemisphere. The projection fibers go up and down, from the hemispheres down to the spinal cord, from the spinal cord up to the hemispheres. And here's what the association fibers look like. This is one hemisphere here, and we communicate front to back to front to back to front, so that every side of the brain knows what the other side's doing. All information that's needed by the cortex is available wherever it's located. So we're using these communication fibers here to tell the same side what's going on, to tell the other side what's going on, to tell the front and back what's going on. So we're always communicating back and forth, back and forth. We know everything that we can about our external and our internal environment. We try very hard to respond to external and internal stimulus effectively, logically, in a healthy manner. One of the structures we use in our brain to do this is the limbic system. The limbic system is essentially our emotional brain. The limbic system includes the thalamus, where all sensory input comes in except odor, the hypothalamus, where we get our odor input by way of the mammillary bodies, the hippocampus, which allows us to store memories. The hippocampus doesn't make memories, but it allows them to get stored. A structure known as the amygdala and cingulate gyrus. The amygdala is essentially our fear response, and the cingulate gyrus is our rage and aggression response. And so the limbic system lays down deals with our emotional response to stimulus and allows us to store memories on how to respond when in certain conditions. How do you respond when you're afraid? How do you respond when you're angry? What's the appropriate way to respond in either condition? And what triggers an emotional response? This is what the limbic system does for us. There's the amygdala right there. The cingulate gyrus is not shown on here. There's our basal ganglia. There's our thalamus. There's the hypothalamus. There's our hippocampus right there. And cingulate gyrus, I'll show you that here in a second. So, okay, the amygdala. The amygdala are paired structures. They are on those, let me go back here and show you this. That little green thing at the end. The limbic system is called limbic because it's a sort of a circular shaped structure, and it has this prong that comes out on each side, terminates in the amygdala. The amygdala allows us to get ready for a stressful or an emergency type situation. We are startled when something unexpected happens in front of us or happens to us, and we store those memories of being startled so we're ready the next time. So that the next time some event occurs, you are prepared for it and not overwhelmed or startled, as they say. The amygdala is the link between a stimulus that may be fearful and how we react. How do we react to a stimulus that has potential harm to us or to friends or family? The amygdala essentially triggers our fear response. And our fear, and it gives us what we call the fear emotion. Okay, now, if our fear emotion overwhelms us, then we move into a panic state. If our fear emotion triggers us to respond the way our memories lay it down, the way we've been trained to respond, then we don't go into a panic. We still do things effectively. The amygdala helps us to store memories on how to respond in emergencies and in emotional situations. How do you respond? How do you respond at the site of an accident, at the scene of an accident? How do you respond when someone is, when someone is, extremely irritated with you and is expressing their displeasure very vocally? How do you respond to that? Are you afraid? And if you are afraid, how do you try to mitigate that? The actions, and the amygdala is the little green things you see here in the animation. The actions on how to respond correctly and incorrectly are based in our memories. We learn them from past experiences. The amygdala has a large part to play in pleasure activities, things that we like to do. They also play a large part in sexual arousal. as males and females mature, the amygdala may get larger depending on sexual activity and as the individual matures. You know, how do they deal with sexual activity? How do they deal with arousal? What gives people pleasure? You know, lots of things do that. So the amygdala is helping the individual to, you know, enjoy doing things, not just sexual activity, but to enjoy doing things. So the cingulate gyrus is just above the corpus callosum. The cingulate gyrus is, you know, the corpus callosum are the fibers that connect side to side. The cingulate gyrus is just above the corpus callosum. It is a pathway from the thalamus to the hippocampus. And the cingulate gyrus allows us to store memories, or at least associate memories to various odors. So when I talk about, you know, how odors can trigger memories and emotional responses, it is the cingulate gyrus that is allowing this to occur, because odors detected by the olfactory receptors and pass through to the temporal lobe of the brain through the mammillary body and the hypothalamus also triggers the cingulate gyrus, and you respond to a pleasant odor, a bad odor. You recognize the odor, because of a memory of it. You may go down another memory pathway of some event associated with that odor. The cingulate gyrus also allows us to express our emotions without having to verbalize them. You know, a gesture, for example. You know, when someone waves at you in the car but forgets to use all their fingers, and just, you know, that someone flips you off, or worse, they make other gestures that are even more inappropriate. Maybe they shake their fist at you. Maybe they wave a gun at you. You know, the cingulate gyrus is triggering that emotional response through some sort of gesture. The cingulate gyrus also does also help us when we have some sort of conflict going on, some sort of emotional or psychological or stressful conflict at work or at home or at school, trying to help you resolve the situation, and we're frustrated. Cingulate gyrus is trying to help us with that. This is unfortunately also the part of the emotional brain that allows us to throw things when we're upset or break things. When someone is so frustrated trying to resolve a problem that they're just, you know, throwing things around, tearing things apart. We've all seen it. We may have experienced it. If nothing else, we've seen it, you know, acted out in TV or in the movies where people are frustrated. The cingulate gyrus is at work. You know, if you've ever seen It's a Wonderful Life, and you know the scene where Jimmy Stewart comes home and he can't even cash in his insurance policy, and the kids are all standing around saying, you know, they want to have their Christmas party, and Donna Reed is just sort of useless standing there, and Jimmy Stewart comes in and he knocks everything off of his desk, destroys all of his models he's built. That's a cingulate gyrus at work, because he is so frustrated. He can't find the answer. They're missing $8,000, if you remember the movie. He can't find the answer, so he starts tearing everything apart. And of course, it doesn't help at all, but that's the cingulate gyrus is responsible for that action. The amygdala is a little different. The amygdala allows us to have a fear response to protect us when necessary. When we perceive that we are in a fearful situation, we can respond to it. We can stand and fight or run away. We can take some sort of action. We have to recognize the fear response. Fear response is there to protect us. The fear response is a biochemical response to external stimulus. So, and that's what it does. It tells us how to respond. So the cingulate gyrus deals with stress and rage and aggression. The amygdala deals with fear and learning how to respond to fear. So two key areas here. Both of them depend on memories being stored through the hippocampus to tell us how to respond. Memories are stored by the hippocampus. Hippocampus doesn't make the memory. And we don't make memories. Memories are a record of the events as they happen. When commercial advertising says, well, let's go make some memories. Well, no, memories, well, how do you make a memory that you like? Do you get a redo if you don't like the memory? Memories are just the occurrence of what happened. You go to the beach and it rains every day and you get no beach time. Well, your memory of that trip will be staying in the hotel all day long because it's raining, or finding other things to do, and you may not have a very pleasant memory of that particular beach trip. Or you may discover that you really had a good time. It just depends. Anyway, let's talk about the primary motor cortex, because this is what's going to be activated to do things for us, whether we're dealing with the cingulate gyrus or the amygdala. Now, in the precentral gyrus, the ridge in front of the central sulcus, we have the primary motor cortex. The primary motor cortex has areas that control motion in all parts of our body on the left side and on the right side. We eventually, these neurons in the primary motor cortex extend to neurons in the spinal cord, which will then ultimately synapse on the skeletal muscles. So a motor nerve controlling skeletal muscle cells is controlled itself by the primary motor cortex and the large neuron that it's using to send signals down to the motor neuron. It gives us voluntary motor control. And of course, these axons are called tracks at this point. These large nerves are really the tracks that we send the signal down. So here is the central sulcus right here. Here is, in this orange area, this dark orange area, is the primary motor cortex. This is where we send, where motor activity signals originate, in the primary motor area. Directly behind the primary motor area, in this this groove here, this ridge area here, remember, this is the precentral gyrus. This is the gyrus in front of that. The premotor area is where we use learned skills, pattern skills, where practice and practice and practice is laid down. We use the cerebellum, of course, to refine all that, but we initiate the motor activity in the cortex. The premotor cortex tells us how to use a keyboard, how to drive our car, how to ride a bicycle. The cerebellum tells us how to do it right. And so any kind of learned skill is stored in the premotor cortex. Any kind of patterned response is learned in the premotor cortex. When we plan activity, how we're going to do something, how am I going to swim across the lake? How am I going to run the hurdles? How am I going to participate in a play in football or baseball or any kind of sport? How am I going to drive my car down the road? Planned movements come out of the premotor cortex. The primary motor cortex initiates the action. The premotor cortex tells us what actions we want to do. And the cerebellum tells us how to do it better. Damage to the premotor area would involve us having to relearn how to do things. So that is the premotor cortex, directly in front of the primary motor cortex. Now, the next area deals with vision. We have the frontal eye field, and we have what's known as Broca's area. The frontal eye field is in that little notched area between the primary and premotor cortex. It's directly above Broca's area. The frontal eye field allows us to move our eyeballs. It controls the muscles around the eye. It also allows us to respond to sound and touch. We turn our head or move our eyes when we hear a sound. We look in the direction of the sound. We look in the direction of some sort of tactile stimulus. That is the frontal eye field. It allows our eyeballs to move. Broca's area it's on the left-hand side only. It's right here, right at the junction of the temporal lobe and the frontal lobe, and right behind the primary motor cortex. This controls our ability to move our teeth and tongue and lips to talk. If your patient has what's known as aphasia, they can't talk, the damage is probably on the left-hand side of the cerebral cortex, because the Broca's area is only on the left side. So a person who is unable to speak after having trauma or a stroke, it's pretty good bet that the damage is somewhere in the left cerebral hemisphere, near the frontal lobe, in the frontal lobe on the left-hand side, because Broca's area is only on the left side. So, okay, that's a good place to stop. Any questions on anything? Okay, then I'm gonna go ahead and pull the plug, and I will see you all next week. And remember, labs are done, by the way, so I'll have to post a 4th lab test for us. So, okay, and I'll see you later.